1200 degrees Celsius. That is the temperature at which iron ore surrenders its structure. Not melts, not softens, surrenders. At 1200 degrees Celsius, the molecular bonds that hold iron ore together, bonds formed over hundreds of millions of years of geological compression, simply release. The material transforms. What was stone becomes fluid. What was rigid becomes capable of being poured, shaped, and cooled into something entirely different. This was 1901. Japan had no native coal reserves in sufficient quantity. It had no established metallurgical tradition at industrial scale. It had no trained workforce for blast furnace operation. It had no hydraulic cranes, no diesel loaders, no electrical instrumentation on the furnace floor. What it had was a decision to build. The Yawata Iron and Steel Works, Kitakyushu, Japan, located on the northern coast of Kyushu Island, where coal could arrive by ship from Manchuria and iron ore from China could be offloaded at the adjacent port facility within the same operational cycle. The plant cost 25 million yen to construct. In 1901 terms, that figure represented approximately one-third of Japan's entire annual national budget. One-third. The first blast furnace at Yawata stood 22 meters tall. Its daily output capacity was 100 tons of pig iron. The internal temperature of the combustion chamber regularly exceeded 1,400 degrees Celsius during peak operation. The coke consumption rate was 1.1 tons per ton of iron produced. The workers who operated it stood on open platforms beside a structure radiating heat measurable from 30 meters away. There was no sensor system. There was no automated shutdown protocol. There was no union. There was no one coming to help if something went wrong on the night shift. This documentary is not about blast furnaces. It is about something the men who ran them understood, something they had to understand about the people standing next to them. Because in a facility operating at 1400 degrees, with 200 kilograms of molten iron moving overhead on a ladle crane operated by a man you may or may not know, trust was not a social concept. It was a structural one. The Japanese rule for choosing friends. Most people today have never heard of it the way it was lived. To understand the rule, you first have to understand the environment in which it was forged. Yawata was not the only facility. By 1910, Japan had expanded its industrial base to include the Mitsui Miki coal mines in Fukuoka, the Mitsubishi Nagasaki shipyards, the Sumitomo copper smelter at Beshi, and the Ashio copper mine, one of the oldest and most dangerous mining operations in the industrialized world. These were not individual factories. They were integrated systems, networks of labor, material, heat, pressure, and mechanical force operating simultaneously across hundreds of interconnected stations. At Miki coal mine alone, the workforce exceeded 10,000 men by 1906. The main shaft descended to over 300 meters below sea level. Gas accumulation was a documented and recurring problem. Ventilation was mechanical, powered by steam-driven fan systems that required constant maintenance from crews working in complete darkness. Let us stay with numbers for a moment. The Beshi copper smelter processed over 3,500 tons of ore per day at peak capacity. The smelting furnaces maintained operating temperatures between 1,000 and 1,300 degrees Celsius. The copper matte produced in the initial smelting phase contained sulfur compounds that, when oxidized, produced sulfur dioxide gas as a byproduct of the process. Sulfur dioxide at concentrations above 5 parts per million causes immediate respiratory distress. The workers inside Beshi operated in environments where ambient SO interleation levels periodically exceeded that threshold. There were no respirators. There were damp cloths. That was the technology. At Nagasaki, the Mitsubishi shipyard was assembling vessels displacing over 15,000 tons. Riveters worked on vertical steel hull sections using hand-driven pneumatic hammers, and heated rivets passed upward from ground level by catcher buoys positioned beneath the scaffolding. A single riveting team consisted of 4 men: the heater, the catcher, the holder-on, and the riveter. Each team placed, on average, between 200 and 300 rivets per 10-hour shift. A dropped rivet from 30 meters at temperature killed, not injured, killed. This was the scale. And within this scale, the Japanese industrial worker of the early 1900s developed something that has been described since then in various ways, as loyalty culture, as group identity, as collectivism. Academics have attached many labels. The men inside these plants called it something simpler. They called it knowing who was next to you. Japan's industrialization did not happen in isolation from economic pressure. The Meiji government's decision to develop heavy industry was rooted in a specific, documented fear that without industrial self-sufficiency, specifically in steel production and shipbuilding, Japan would remain technologically dependent on Western powers indefinitely. This was not paranoia. It was accurate. In the 1890s, Japan imported virtually all of its structural steel. Naval vessels were constructed in British and French shipyards. Railway locomotives came from the United States and Germany. The raw materials existed domestically but could not be processed at scale with the technology then available. The Sino-Japanese War of 1894 to 1895 exposed the problem structurally. Supply chains for military materials ran through foreign ports. Delivery time lines were dependent on shipping companies that had no particular obligation to prioritize Japanese military contracts over more profitable civilian ones. The industrial expansion program launched under the late Meiji period was, at its core, a logistics problem being solved with metallurgy. You needed steel. To make steel at scale, you needed blast furnaces. To run blast furnaces, you needed coke, ore, water, and men. The men were the variable you could not standardize with engineering. Here is where the operational challenge becomes relevant. Blast furnace operation is a continuous process. Unlike a textile mill or a lumber yard, you cannot simply stop a blast furnace between shifts, lock the door, and resume the next morning. Once a furnace is brought to operating temperature, a process that itself takes 24 to 48 hours and consumes enormous quantities of fuel, it must remain in operation continuously. Shutdowns were expensive, took days to reverse, and introduced thermal stress into the refractory lining with each cycle. Iwata's furnaces ran continuously. That meant 3-shift rotation. Day crew, evening crew, night crew. And what that meant in practice was that the man who was supposed to monitor the gas seal on the charging bell during the 2 a.m. fill cycle, while the charge of coke, sinter, and limestone was being added from above, was the man who had been doing the same task for the previous 6 nights. Not the engineer, not the supervisor, the man you worked with. You chose that man, or you accepted whoever was assigned to stand there. The ones who survived long enough to have opinions on the matter developed a very specific framework for that choice. To understand why the selection of a workmate was a mechanical question and not a social one, you have to understand what failure actually looked like in these environments. Start with the blast furnace. The basic operating principle is not complicated. Iron ore, coke, and limestone are loaded to the top of the furnace, the charging bell, in carefully measured proportions. The ratio matters. Too much ore relative to coke, and the combustion temperature drops below the threshold needed to reduce the iron oxide. Too much coke, and you waste fuel and introduce excess carbon into the iron. Preheated air, called the hot blast, is injected into the furnace through tuyers positioned near the base. The combustion of coke in the presence of this forced air generates carbon monoxide, which rises through the burden of ore and flux, and chemically strips the oxygen from the iron oxide molecules. What remains, reduced iron, sinks toward the base of the furnace due to density and temperature differential. At the bottom of the furnace, the iron collects in the hearth. Above it floats molten slag, the calcium silicate waste material formed from the limestone reacting with impurities in the ore. Both are tapped periodically through tap holes drilled with pneumatic lances. The iron flows through troughs into a casting house floor, where it cools in sand molds into what are called pigs, individual ingots of crude iron averaging 40 to 50 kilograms each. Now here is where human placement became mechanically critical. The charging operation at the top of the furnace required coordination between the man operating the skip hoist, the inclined conveyor that carried the material to the top, and the man managing the charging bell sequence at the furnace crown. If the bell was opened at the wrong moment, while pressure inside the furnace was higher than atmospheric, the gas seal failed. Blast furnace gas. This is not steam. This is a mixture of carbon monoxide, carbon dioxide, nitrogen, and hydrogen. Carbon monoxide at concentrations above 35 parts per million causes measurable physiological impairment. At 200 parts per million, it produces headache and disorientation within 2 hours. At concentrations above 1200 parts per million, loss of consciousness occurs within minutes. Above 6,400 parts per million, death within 10 to 15 minutes is well documented in the accident records. Blast furnace gas was colorless. It had a faint odor that many workers reported being unable to detect after prolonged exposure, likely due to habituation or olfactory desensitization. You could not smell it reliably. You could not see it. What you could do was trust the man beside you to tell you the pressure reading before you opened the bell. At the tapping floor level, the geometry of failure was different. The tap hole was opened with a pneumatic drill, driving a steel rod through the clay plug that sealed it between casts. When the tap hole broke through, iron, at approximately 1,450 degrees Celsius, flowed outward under hydrostatic pressure. The flow rate of a typical cast was roughly 3 to 5 tons per minute. If the iron trough had water in it, from rain, from leakage, from improper preparation, the contact between molten iron and water produced a steam explosion. The technical term is a steam explosion because that is what it was physically, water converting to steam faster than the surrounding environment could contain the pressure of the phase transition. The practical result was that 1,450-degree iron moved in directions it was not supposed to move. You prepared the trough. The man you worked with knew that you prepared it correctly. If he didn't know that about you, with certainty, he was standing 40 meters away. Iwata sits on the northern coast of Kyushu. In winter, the wind off the Kanmon Strait carried moisture from the Sea of Japan across the plant site. Temperatures dropped to near zero. The steel structures of the casting house condensed that moisture overnight. By morning, the charging platform was slick. The slag pots, open-topped ladles holding 10 to 15 tons of molten slag at temperatures above 1,300 degrees, were moved by overhead crane through this same environment. The crane operators worked in unheated cabs above the furnace line. The noise level on the casting floor during a tap was not something that can be adequately rendered in description alone. The roar of the hot blast tuyers, the grinding of the skip hoist mechanism, the hammering of the drill on the tap hole clay. The combination exceeded 100 decibels routinely. Workers communicated by signal, by gesture, by predetermined sequence. Verbal communication was not possible at working distance. Inside the mine shafts at Mike, the conditions were inverted. Where Yawata was open to sky and wind, Miike was enclosed. The temperature underground increased with depth, roughly 3 degrees Celsius per 100 meters. At 300 meters below surface, ambient rock temperature was significantly above surface temperature, and the combination of humidity from groundwater seepage and heat from the rock made the working environment comparable in physiological stress to extreme outdoor summer heat. The lighting was oil lamp. Each miner carried his own. The gas detection method was a canary. When the canary stopped moving, you had a finite amount of time to make a decision about direction. The man nearest you needed to have made that decision correctly before. You needed to know that about him. The noise in the shaft during active cutting, the steam-powered cutting machinery, the chains, the coal cars on the iron rails meant that warning shots from one section did not reliably carry to another. You communicated with the people immediately adjacent to you. Everyone else was effectively in a separate operational unit. At the Nagasaki shipyard, the environment was vertical. The hull sections of a naval vessel rise 15, 20, 30 meters from the keel to the deck rail. The scaffolding on which the riveters worked was timber and rope construction, installed new for each vessel and removed at completion. It was not engineered for the loads it carried during active riveting. Pneumatic hammer vibration transmitted to the scaffold platform continuously during working hours. A riveter on a platform 25 meters above the dry dock floor, driving a rivet in a horizontal seam, while his partner on the inside applied the bucking bar to hold the rivet head against the plate. That operation required both men to work with perfect timing, against the same rivet simultaneously. If one stopped without signaling, if one slipped, if the platform moved, if a tension broke at the wrong moment, the rivet failed. A failed rivet on a ship hull meant a void in the structure. In a naval vessel, structural voids had consequences that extended far beyond the shipyard. Cause. These men understood something about selection that has been diluted significantly in the time since. The accident record from Japanese industrial facilities in the period between 1901 and 1930 is substantial and largely underreported in Western industrial history. Let the numbers carry the weight. In 1907, an explosion at the Hojo coal mine in Yamaguchi Prefecture killed 365 men. The cause was fire damp, methane, ignited by an open lamp. The ventilation system had been reported as inadequate by mine workers 6 months prior. The report was filed. The inadequacy was not corrected before the explosion. In 1914, a steam boiler rupture at a paper mill in Ehime Prefecture killed 11 workers and destroyed the boiler room. The boiler had been operating at a documented pressure above its rated capacity for a period that, based on maintenance records, extended to at least 2 weeks prior to failure. In 1916, a molten metal spill at the Kamaishi Iron and Steel Works, a facility predating Yawata by several decades, resulted in serious burn injuries to 7 workers and 1 fatality when a ladle crane operator lost control of a suspended crucible during transfer. The crane mechanism had a documented maintenance deficiency in the bridge drive gear system. The crew assigned to that shift had not been informed. These are not isolated incidents. These are the documented ones. The undocumented workplace injuries in this period, the crushed hands, the heat exhaustion, the carbon monoxide poisoning events that did not result in fatalities and therefore did not generate formal reports, were by any reasonable estimate many times higher than the recorded figures. A survey of Japanese industrial accident statistics conducted in 1920 by the Ministry of Agriculture and Commerce found that the heavy industry sector recorded 9.4 serious injuries per 100 workers annually. Fatality rates in underground mining operations range from 1.2 to 2.4 deaths per 100 workers per year depending on the facility. Now consider what those numbers meant in operational terms. If you were assigned to a work crew of 8 men in a coal mine, operating continuously for 12 months, the statistical probability that one of those 8 men would not complete the year intact was not negligible. It was approximately 10 to 20% for serious injury. It was 1 to 2% for death. In a crew of 8, working together for 12 months, that translated to a meaningful probability of watching someone you worked beside get hurt or not come back. The men in these facilities understood this, not as abstract risk, as daily operational context, and the understanding of this context, the daily, undeniable, mechanically verifiable understanding that the person next to you might be the last line of defense between you and a very specific physical outcome, created a method for assessing other people that was not social in origin. It was functional, it was systematic, and it was rigorous in ways that have been significantly softened since the environments that produced it no longer exist in the same form. Here is what failure looked like at each major hazard point. Boiler rupture. A fire tube boiler operating at 15 psi maintains approximately 10 times atmospheric pressure inside the vessel. The water inside is heated above its atmospheric boiling point and exists in a liquid state only because of the pressure containing it. When the vessel wall fails, through corrosion, through mechanical defect, through operator error in pressure management, the water flashes to steam instantaneously. The volume expansion ratio of water to steam at atmospheric pressure is approximately 1,700 to 1,000. Inside a ruptured boiler shell, that expansion has no controlled outlet. The shell fragments. It does not leak. It does not crack. The metal moves at velocity. Men working at the boiler front, the firing end, where fuel was loaded, were in the primary fragment zone. There was no armored barrier between the fireman and the boiler front. There was the boiler. Carbon monoxide accumulation in sealed or semi-enclosed spaces, the underground headings of a coal mine, the enclosed sections of a blast furnace gas recovery system, the interior of an unpurged vessel before hot work. CO could accumulate to lethal concentrations without any visible or immediately olfactory indicator. The first symptom is headache. The second is confusion. The third is the inability to form the decision to leave. The progression from first symptom to incapacitation at concentrations present in an enclosed space following a gas seal failure was documented at under 10 minutes in multiple fatality investigations, track and haulage failures. In the underground rail haulage systems of mines like Miki, coal cars operated on narrow gauge iron rails through tunnels often less than 2 meters in height. The grade of the incline haulage sections could reach 1 in 8 a 12-degree slope. The braking system on the descending inclines was mechanical, a hand-operated brake applied by the driver. If the car broke free, if the brake mechanism failed, if the coupling detached, the loaded car traveled down the incline at whatever velocity the grade and length allowed. Men working at the bottom of the incline had the warning time provided by the noise of the steel wheels on the iron rail. In sections of track around corners, that warning time was 0, molten metal contact. The burn injury severity from molten iron or steel contact is not comparable to thermal burns from fire or steam. Liquid iron at 1450 degrees carries enough thermal energy to ignite clothing instantaneously and to penetrate skin through to underlying tissue faster than any pain signal can reach the brain rapidly, enough to produce a protective reaction. The men who worked the casting floors knew this. They developed a specific way of moving, deliberate, measured, always with one eye on the iron's path. Not because they were trained to, because the ones who didn't move that way were not present for the lesson twice. The workforce of Yawata's early years was drawn primarily from the rural prefectures of Kyushu, Fukuoka, Saga, Nagasaki, Kumamoto, supplemented by experienced workers recruited from older mining and smelting operations in Iwate and Akita prefectures. Daily wages for unskilled laborers in 1901 averaged between 15 and 25 sen. A skilled furnace operator, what would today be called a process technician, might earn 50 to 80 sen per day. For context, a bowl of soba noodles in 1901 cost approximately 1 to 2 sen. The wages sustained a subsistence existence without significant margin. Workers were housed in company dormitories at facilities like Yawata and Miki. This was not a benefit in the modern sense. Company housing meant company control of where you lived, company stores that controlled where you spent your wages, and an economic relationship between worker and employer that extended far beyond the working shift. The working shift at Yawata was 12 hours, 2 shifts per day. The furnace ran continuously, so the transition between shifts, the handover of operational responsibility from one crew to the next, was itself a critical safety interval. Everything the incoming crew needed to know about the furnace's current condition had to be transferred verbally, in the noise of an operating cast house. In the time between one crew stepping off the platform and another stepping on, there was no written handover log in the early years. There was conversation. There was what the outgoing man told the incoming man. The Japanese industrial workforce of this era operated within a deeply stratified crew system that was both organizational and social. Senior workers, called oyakata in many facilities, functioned as labor contractors as much as supervisors. They recruited their own crews, trained them within the crew, maintained discipline within the crew, and were held responsible for the crew's output and safety record. The oyakata chose. This was not incidental. The oyakata system produced as a structural byproduct an extremely practical framework for evaluating people that predated any formal articulation of it. Here's what they observed. Not personality. Not whether someone was agreeable or pleasant or good company at the dormitory. Those qualities were relevant at 1400 degrees. What they observed was behavior under pressure. Specifically, behavior at the moment when the correct action was costly to the individual performing it. Does the man report a problem before it becomes a crisis, knowing that reporting it means more work for himself? Does the man hold his position when the situation becomes dangerous? Or does he retreat and leave the gap in the crew's coverage? Does the man maintain his technical precision when he is fatigued? When the shift has run 10 hours and the coke charge ratio still needs to be correct at hour 11? Does the man tell you the truth about what he observed on the previous shift, even when the truth reflects poorly on decisions he made? These were the criteria, not articulated as a formal system, applied as standard operating practice. And here's where the rule that is most consistently misapplied becomes clear. The men who ran these facilities, the oyakata, the senior operators, the men who had survived long enough to have selection authority, were not choosing companions. They were choosing the people whose judgment would affect the physical reality of their own survival. That is a different selection problem than choosing someone to spend time with. It requires a different set of observable data. Most people applying any version of this rule today make the same error. They select based on affinity, shared interests, comfortable conversation, similar background, the absence of friction. The oyakata selected based on demonstrated function under documented conditions. The distinction is not subtle. It is the difference between choosing someone you enjoy and choosing someone whose behavior you have observed in circumstances where behavior is expensive to fake. The Japanese concept being referenced here in modern discussions often traces to Confucian influence on social structure, specifically the 5 relationships of classical Confucian ethics, in which the relationship between friends is one of the 5 primary bonds, carrying mutual obligation of honest counsel. A friend, in this framework, is not someone who agrees with you. A friend is someone who tells you what is accurate, even when accuracy is unwelcome. In the blast furnace context, this was not philosophy. It was calibration. If the man beside you told you the pressure reading was safe when it was not, for any reason, including the reason that he was tired or distracted, or simply wrong, the physical consequence was your problem, your lungs, your skin, your life. Truth-telling was not a virtue preference. It was a functional specification. The blast furnaces of early Iwata were not built to last indefinitely. They were built to function at maximum output within the material limits of their construction. The refractory lining, the fire brick and castable ceramic material that separated the iron-bearing burden and the 1400-degree combustion gas from the steel shell of the furnace, wore continuously. During operation, the thermal cycling of each working day expanded and contracted the lining materials differentially, creating micro-cracks that accumulated over time. The abrasive action of the descending burden material, the coke, ore, and limestone charge moving slowly downward under gravity as the iron reduced and sank, eroded the lining from the inside. A new furnace lining lasted, depending on operating practice and material quality, between 3 and 5 years before requiring a full reline. A reline required complete shutdown, complete cooling, a process taking 2 to 3 weeks, physical entry into the furnace interior, removal of the old refractory material, and installation of new fire brick, which itself required drying and curing time before the furnace could be brought back to operating temperature. The men who performed the reline work entered a furnace that had been operating at 1,400 degrees continuously for years. The lining, when removed, was saturated with the residue of everything that had passed through it: carbon deposits, alkali compounds that had volatilized from the ore and recondensed in the upper furnace zones, zinc compounds from trace impurities in the ore charge. The demolition of the old lining produced dust that contained these materials. There were no dust masks rated for refractory demolition. The working conditions inside a furnace during a reline were among the most physically demanding and hazardous of any task in the steelwork. The men who did it were not specialists. They were the labor pool assigned. Bearing lubrication was another continuous maintenance requirement that, when neglected, produced consequences proportional to the system being lubricated. The main drive shaft on the skip hoist at Iwata rotated at several hundred RPM continuously during charging operations. The bearings supporting that shaft were grease-packed, manually repacked by maintenance workers during shift intervals. If the grease interval was missed, the bearing temperature rose due to increased friction, which reduced the viscosity of the remaining lubricant, which increased friction further. A seized bearing on a skip hoist mechanism during active charging could drop the loaded skip. A loaded skip weighed several tons. The track it traveled was directly adjacent to the furnace crown platform. The riveted construction of the furnace shell itself presented a separate long-term integrity problem. Individual rivets could be checked visually for head condition and driven condition. What could not be checked visually, without removing them, was the condition of the shank passing through the plate. Corrosion from the outer surface of the furnace shell, particularly in the stack section, above the tailleur zone where condensation of process moisture was possible, could attack the rivet shanks over years of operation. Shell integrity failures in riveted construction did not happen suddenly from a single event. They developed over time through accumulated fatigue, through corrosion working in hidden geometry, through stresses that no visual inspection could measure. The engineers at these facilities knew this. The inspection schedules they could implement were limited by what was observable from outside. The lesson is specific. These machines, as large, as powerful, as economically important as they were fragile in ways that the scale itself obscured. The 22-meter furnace that produced 100 tons of iron per day was held together, at a fundamental level, by refractory brick that eroded at measurable rate, by rivets that corroded in hidden sections, by bearings that needed manual attention on a schedule that could not be missed. The maintenance crew understood this fragility better than anyone, and the men who selected their work partners understood something analogous about people. The most capable worker, the most technically skilled, the most physically capable, the most valuable in terms of output, could develop hidden deficiencies that the surface presentation did not reveal. Fatigue accumulated unseen. Judgment eroded under conditions of sustained stress. Attention failed in predictable ways. The Oyakata who had been in the facility long enough understood that selecting a man based solely on his apparent output at a given moment was equivalent to selecting a furnace lining based on its initial installation quality without accounting for wear rate. What mattered was how the function held over time, under repeated stress cycles, under conditions the initial evaluation could not simulate. This is the part most people get wrong when applying the concept today. They evaluate at a moment. The industrial rule was always about trajectory under load. By 1910, Yawata was producing 60% of Japan's total steel output. By 1913, Japan had become the seventh largest steel producer in the world. This was not a trivial acceleration. In 1895, Japan produced essentially no significant quantity of domestically manufactured structural steel. 15 years later, it was producing enough to supply its own naval expansion program, its railroad construction program, and the beginning of domestic heavy machinery manufacturing. The Russo-Japanese War of 1904 to 1905 provided the first large-scale test of domestic industrial capacity. Japanese steel was in the hulls of the vessels that fought at Tsushima. Japanese coal from Miki was in the bunkers of those vessels. The economic implication was not only military. Railroad expansion across Japan through the late Meiji period consumed enormous quantities of steel rail. The standardization of rail gauge, a decision made for operational efficiency reasons, required that all rail material meet consistent dimensional and metallurgical specifications. Domestic steel production made those specifications controllable without foreign supply chain dependence. The cities that grew along those rail lines, the industrial prefectures of Aichi, Hyogo, Osaka, grew in direct correlation with the steel production capacity that supplied their construction. The Sumitomo copper operations at Beshi provided the electrical conductor material for the telegraph and early telephone networks. The Mitsubishi shipyards at Nagasaki produced the vessels that connected Japan's domestic coastal trade. The economic architecture of modern Japan, its industrial geography, the distribution of its manufacturing capacity, the layout of its rail network, the location of its major ports, was physically determined by decisions made about where to site blast furnaces, how to route coal, where to dig mines. The men operating those machines were the functional units of that economic construction. Their selection, who worked with whom, who could be trusted to hold a tap-hole position correctly, who would report a bearing failure before it became a hoist failure, was part of the operational logic of the system. The rule for choosing people in this environment was not separate from the economic function. It was embedded in it. The blast furnace technology and operating methods of the early Yawata period remained largely stable through the 1920s. The furnaces grew larger, the hot blast temperatures increased with improved stove design. The material handling systems incorporated electric cranes and electric conveyors to replace steam-powered equivalents, but the fundamental process, co-combustion, thermal reduction, gravity separation, tap-hole casting, remained unchanged. The Oyakata crew system persisted through the interwar period, though it came under increasing pressure from labor organizing and management reform movements that sought to replace the contractor-based labor model with direct employment. The 1920s brought a series of significant labor disputes to Japanese heavy industry, the Kawasaki and Mitsubishi shipyard strikes of 1921 being among the most significant. The disputes were about wages and working hours primarily. They were also, structurally, about who controlled crew selection. The shift away from the Oyakata system, completed through labor law reform and management reorganization over the 1920s and 1930s, changed the mechanism of crew formation. Workers were assigned by management, not selected by senior operators. The practical selection logic did not disappear. It went informal. Senior workers still evaluated the people working beside them. They still applied observable criteria, but the authority to act on those evaluations, to formally include or exclude someone from a crew, had been transferred to management processes that did not share the same proximity to the furnace floor. The post-World War II period brought the replacement of the direct labor model in most heavy industrial facilities with what became the Kairetsu employment system, lifetime employment, seniority-based advancement, deep internal training programs. This system produced its own form of long observation selection. In the Kairetsu model, you worked with people for decades. The evaluation horizon was long enough that the kind of cumulative observation the Oyakata applied across crew cycles was embedded in the organizational structure itself. You could not remain in a Kairetsu company for 20 years and maintain a full service presentation. The organizational structure enforced, over time, the same kind of deep observation the dangerous environment had enforced more rapidly. By the 1950s and 1960s, automation had begun to reduce the direct human exposure at the most hazardous interfaces. Tap-hole opening moved to automated drill systems. Crane operation moved to remote-controlled cabs separated from the furnace radiant heat zone. Gas detection moved from sensory cues and canaries to electrochemical sensors and continuous monitoring systems. The environment in which the rule had been developed, where the physical proximity of another person's judgment to your own physical safety was inescapable, had been partially mediated by technology. The rule itself became harder to teach because the conditions that had made it self-evidently necessary were no longer universally present. It became a thing that older workers described, that supervisors referenced in training, that was quoted without the industrial context that had given it the weight of mechanical necessity. This is the phase in which most people encounter it now, as a social principle with historical references attached, rather than as the operational output of environments where the wrong choice and selection had physical consequences that were immediate, irreversible, and mechanically explicable. The Iwata Iron and Steel Works continued operating through the 20th century. It merged with other Japanese steel producers to form Nippon Steel in 1970, one of the largest steel companies in the world by output. The original furnace complex from the 1901 construction, or what remains of it, was designated a UNESCO World Heritage Site in 2015. As part of the sites of Japan's Meiji Industrial Revolution, the structure there remains as a shell. The heat is gone. The gas is gone. The men who stood on the charging platform in 1905 in darkness and noise, making a 12-hour shift work correctly, they are gone. The steel they produced is still present in structures built from it. The Beshi copper mine closed in 1973 after nearly 300 years of operation. The Miki coal mine ceased operations in 1997. The Nagasaki shipyard still operates, though at capacity and with workforce levels that bear no resemblance to the 1910 figures. What persisted is not the machines. What persisted is the framework those machines produced as a byproduct of requiring people to rely on each other with mechanical precision. The principle that the selection of people whose judgment is proximate to your own functioning is a technical problem requiring technical criteria, not a social problem requiring social comfort, has been transmitted in distorted form into management literature, into productivity culture, into self-improvement discourse. The distortion is consistent. It softens the observation criteria. It replaces the question, has this person's behavior held under conditions where it was costly to perform correctly, with the easier question, does this person seem aligned with the values I hold? Those are not the same question. The first question is observable and produces verifiable evidence. The second question is interpretive and produces affinity bias. The Oyakata did not ask who shared their values. They asked who had stood correctly at a tap hole at 2:00 in the morning when the cast ran long, and everyone on the floor was at the end of a 12-hour shift. They asked whose information they could operate on. They asked who had told them something true that was inconvenient. The modern version of this rule, as it circulates in simplified forms, usually attributed to Japanese business philosophy or to Confucian wisdom or to some combination of both, typically summarizes to something like, be careful who you allow close to you, because proximity shapes function. That summary is not wrong, it is simply incomplete, because the version of it that emerged from facilities like Iwata and Miyake was not primarily about protecting yourself from bad influence. It was about selecting for people whose function, specifically whose willingness to be accurate in high-cost moments, was confirmed by observation. The criteria that matter are not warm. They are not comfortable to apply. They require observing people in circumstances where correct behavior is not rewarded in the moment. They require waiting longer than affinity allows, because affinity produces data quickly and accurate functional data requires time and stress conditions to emerge. Most people do not wait. They select early based on surface presentation. They find out later, in the equivalent of a midnight shift beside a gas seal, what the person they selected was actually made of. The Oyakata had already made that discovery before committing to a crew. That is the rule. That is the part that gets wrong in every version of it that has been smoothed and simplified and made palatable enough to put in a social media post. The men of the Iwata blast furnace floor did not choose their friends. They selected the people whose functional precision they had documented. And then, after enough shifts together, after enough accurate information exchanged at cost, after enough moments where the other man held his position and told the truth, some of those people became friends. That was the sequence, not the reverse. The furnaces at Iwata were designed for a working life of decades. They were operated by men who were chosen by men who were understood what working life actually meant. The ore ran out. The coal reserves depleted. The process was automated. The hazard was engineered away. What the environment had built, The methodology for selecting the people standing next to you outlasted the environment itself. The original furnace shell stands in Kaitikushu, behind UNESCO preservation barriers, photographed by tourists. The heat it produced is in the steel of buildings that no one connects to Yawata anymore. The men who produced it are in ground that did not have surnames attached to the production records, and the rule they lived by, the one that required no philosophical discussion because the blast furnace enforced it on its own terms, that rule is still here, operating on whatever environment currently demands that the person beside you function correctly when function is expensive. Not pause. It did what it was built to do, and then it was replaced.